So today I'm going to be talking about integration with trig substitution, and this is going to be a technique that you can kind of put in your calculus tool belt, if you want to think of it that way, to solve integrals that otherwise we might not be able to solve. So this is just a new method that allows us to solve more complicated integrals, or integrals that we would previously look at and be like, oh, I have no idea how that's going to work. Okay, so as the name might imply, we're going to have to draw a triangle, right? Because this involves trigonometry. So I have our first example here, the integral of square root 9 minus x squared divided by x squared times dx. And there are three parts to this integral. We have the square root part on the top, we have the x squared on the bottom, and then we have a dx. And what we're going to do is, well, I'll just jump right in. We're going to have to draw a triangle. And it's not just any triangle. The way that we build this triangle is going to allow us to substitute some of our x's and our dx's for trig functions in terms of theta instead of in terms of x. Okay, so I guess the trick here is to draw the triangle in such a way that you can actually substitute the square root part, this x part, and the dx part successfully and eliminate all of the x's and replace them with some function of theta. Okay, so I'm just going to show you how that's going to work for the first example. Here's what we're going to do. We're going to label this angle here theta. This is a right triangle. You cannot tell by my drawing, but this is in fact a right triangle. Okay, so we have our angle theta here, and if I put x here and I put 3 here, everything should work out smoothly, and you will soon see why. Okay, so what we're going to do is we're going to use Pythagorean theorem to find this missing side down here. And if you recall Pythagorean theorem, it's going to leave us with this side is square root 9 minus x squared. Okay, that looks a lot like the top of our fraction in the integral, doesn't it? And that was intentional. Okay, so I designed this triangle, and I put the x and I put the 3 there in a particular place intentionally so that the missing side would be square root 9 minus x squared, and so that that piece would line up with the top of our fraction inside of our integral. Okay, once we have done that, I'm going to write out, well, it looks like the cosine of theta might actually be a useful quantity for us, because the cosine of theta is going to be square root 9 minus x squared divided by 3. Right? Adjacent divided by hypotenuse. I'm just using SOHCAHTOA here. Okay, then if we multiply both sides by 3, wow, we will find out that 3 cosine of theta is equal to square root 9 minus x squared. Okay, so this is the first part of our substitution. The top of our fraction is now going to say 3 cosine theta instead of square root 9 minus x squared. Okay, so I'm going to leave that alone for a moment, and because we want to have an x squared as well on the bottom of the fraction, I think that the sine of theta is going to be a useful quantity. So sine of theta, that's opposite over hypotenuse, so that's going to be x divided by 3. We can multiply both sides by 3 and get 3 times sine theta equals x. And then we could just square both sides, and we get 9 sine squared of theta is equal to x squared. Okay, so now the bottom of our fraction, instead of saying x squared, is going to say 9 sine squared of theta. Now the only part that we have left to calculate is dx. And you can't just put a d theta there because x and theta are related, but dx is not exactly equivalent to d theta. So anyways, basically what we're going to do is we're going to take this piece here off to the side because it already says x is equal to. So x is equal to 3 sine of theta. And we're just going to derive both sides. So the derivative of x is like 1 dx. And the derivative of 3 sine theta is 3 cosine theta times a d theta. Okay, so now this is our third part of our substitution. Instead of writing dx, we will write 3 cosine theta d theta. Okay, so I'm going to go ahead and erase everything on the screen that I don't need immediately to do the substitution. So basically we have our 3 parts here. And I'm going to go ahead and rewrite this integral in terms of theta. And so the way that's going to work is square root of 9 minus x squared. Well, that's actually the same thing as 3 cosine of theta. Sorry for my handwriting. I'm not sure what's going on with my tablet today. Divided by x squared. Okay, so instead of writing x squared, I'm going to write 9 sine squared of theta. And then this was all times a dx. So instead of writing dx, I'm going to write 3 cosine theta times d theta. Okay, I am then going to simplify this a little bit by moving this 3 cosine of theta onto the top of our fraction. So basically what we're going to have is 9 cosine squared of theta divided by 9 sine squared of theta times the d theta. Okay, I'm going to go ahead and erase these 3 pieces here. I don't think we need them anymore. Maybe we do, I don't know. Okay. Well, obviously these 9s are going to cancel out. 9 divided by 9 is just 1. And we would be left with the integral of cosine squared divided by sine squared of theta times d theta. If you recall back to your pre-cal days, cosine divided by sine is actually cotangent. So this whole thing is actually the integral of cotangent squared theta times d theta. And then I think we have to do one more substitution because the integral of cotangent squared is, well, it's unsolvable. We don't know what it is. But we know that the cotangent is actually the same as cosecant squared minus 1. So we'll go ahead and make that substitution. And then we actually do know what the integral of cosecant squared is, and it's negative cotangent. So this is going to be negative cotangent of theta. And then the integral of 1 with respect to d theta is just theta. And then we have plus some arbitrary constant. Okay, so we've actually successfully solved the integral. Now the only problem is our original answer had x's in it, and the original question had x's in it, and we don't have any x's. We're still working with theta. So what we're going to do is go back from thetas to x's. And I guess that is actually going to require us to have our triangle back, so we'll draw it here. 3. Okay, so the cotangent, or the negative cotangent, is a pretty simple substitution because that's just the adjacent side divided by the opposite side. So what we're going to have is negative and the cotangent is going to be square root 9 minus x squared over x. And then theta, that's a little more tricky, right? Well, we know that the sine of theta is equal to x over 3, or 1/3 of x. Multiply both sides by 3 again. 3 sine theta equals x. Oh, wait, no, I don't know why I said that. Basically, we're just going to inverse sine both sides right now. So that would tell us that theta is equal to the inverse sine of x over 3. And that looks pretty weird, but we're just going to put that right in the answer, right? So instead of minus theta, we're going to say minus the inverse sine of x over 3 plus some constant. Okay, and this is going to be our answer. Wonderful. Okay, so I will do another example here in just a second. Let me clear everything out. Okay, so here we are with another example of an integral that we probably couldn't solve any other way, so we're going to have to use trig substitution. So, first thing I'm going to do is try and draw my triangle. Again, I'm going to try and draw the triangle in such a way that I can get the x squared, I can get the square root of x squared plus 4, and maybe even get a dx out of it, if possible. Okay. So here's my triangle. Here's theta. This time I'm noticing the square root of x squared plus 4. Like last time it was a subtraction, this time it's a plus. So I think what that means for us is that we need to put a 2 here and an x here so that the hypotenuse will be square root of 4 plus x squared. Again, this part is just Pythagorean theorem, right? I filled in the first two, and then I applied Pythagorean theorem to find the missing side. Okay, so in my opinion, we can get an x squared. Obviously, we can get a 4 plus x squared, and I think we can also get a dx. So the first thing that I'm going to do is write that the tangent of theta is the opposite over the adjacent, so that's going to be x over 2. That means x is going to be 2 tan theta. That's great. Okay, so what I'm going to do now is I'm going to hang on to this, but I'm also going to derive both sides, because if we derive the left-hand side, that would give us a dx. And we also need a dx. So anyways, the derivative of tangent is secant squared. Did I say that right? Yes, it is secant squared. Okay, so this is going to be 2 secant squared theta times the d theta. Okay, I'm going to hold on to this 2, right? We've already got 2 out of our 3 pieces. And let's see. To get that third piece, 1 over square root x squared plus 4. Well, I think the best we could do is probably the cosine. So cosine of theta is equal to adjacent over hypotenuse, so that's going to be 2 over square root of 4 plus x squared. Okay, so if we divide both sides by 2, we'll get 1/2 of the cosine of theta is equal to 1 over square root 4 plus x squared. Okay, so that's pretty good, right? Actually, I might rename this 1/2 of cosine theta. Cosine theta over 2. The reason I'm doing that is because I could tell by looking at the integral that we're going to have to put some things into fractions. So I just went ahead and made the cosine divided by 2. I just made that into one fraction. Okay. So I believe this is going to be, the 3 pieces that I've circled are going to be the 3 pieces that we're going to need to substitute into this integral here at the top. So I'm going to erase everything that we don't need. I'm actually going to keep the triangle this time because it turns out we're going to need that again at the end, right? Okay. So we have integral. Now we know that the 1 over square root x squared plus 4 is actually going to be cosine theta divided by 2, and 1 over x squared is going to be 1 over 2 tan of theta squared, and then dx is going to be 2 secant squared theta times d theta. Okay. Now, I think what we need to do is just take a moment to look at our trig functions here, the cosine, the tangent squared, and the secant squared, and just see if we can simplify them a little bit. So I'm going to go ahead and go down here, and it looks like what we have so far is 2 cosine theta secant squared theta over 8 tan squared of theta, and then times d theta. Okay, so I just recombined all these trig functions into one fraction. That's all I did. I squared this piece, which gives you 4 tan squared, multiplied by 2, that gives you the 8. Okay. Still, this is quite a complicated integral, so I'm thinking that, what am I thinking? Well, I know for sure that since secant is 1 divided by cosine, that one of these cancels out one of these. And I also know that 2 over 8 is the same thing as 1/4, so we can already simplify that a little. And because 1/4 is a constant multiple, we could even put that outside the integral. Okay, so all these things will be helpful, and then we're just going to be left with secant theta over tan squared of theta times d theta. I'm going to go ahead and erase my 3 substitution rules here. Okay. I'm going to expand my tangent into sine over cosine. So we're going to have 1/4 of, actually I'm going to take this over to the side. Secant theta is 1 over cosine theta, and then we're dividing that by tan squared, so that's going to be sine squared over cosine squared. And if you recall, dividing by fractions is the same thing as multiplying by the reciprocal. So we got 1 over cosine times cosine squared divided by sine squared. Now again, this one is going to cancel out one of these. So what we're left with is cosine divided by sine squared. And that's even better, right? Now, this is where it's going to get weird. Okay, so this fraction here, to integrate it, we're going to have to do a u substitution. So we're going to remember that if we make u equal to sine of theta, then du is going to be cosine theta times d theta. So then what we're going to have is 1/4 integral of du divided by u squared, or 1/4 integral u to the -2 times du. And this is actually pretty easy to work out. It's -1/4 u to the -1. And then we plug in sine theta for u. So we get -1/4. Oh, I'm sorry, this should be plus a constant, right? -1/4 sine theta to the -1 plus a constant. Okay, I'm going to again erase some things that we don't need anymore. Okay, so what we have is this integral so far is equal to -1/4. Sine to the -1 is actually just going to be 1 over sine plus some constant. And then 1 divided by sine is actually cosecant, so we have -1/4 cosecant of theta plus some constant. And then to get back to our x, right, our original question had x's in it, so we need to now get rid of the thetas and replace them with x's. So cosecant is 1 divided by sine, or the reciprocal of sine, so that's going to be -1/4 times square root 4 plus x squared divided by x plus the constant. There is your answer. Okay, so this topic is a little complicated. There's quite a few steps. But if you can try and break it down into the sub-steps, it's going to be a little bit easier. Right, so maybe we should talk about that. Like, what are we doing? What is the broad scope of this project? Step 1 is to draw a triangle. Step 2 is to simplify your integral. And by simplify, I mean we're turning it into something with theta. 3, you go ahead and do the integration with theta. And then 4, you want to turn your thetas back to x's. So this is basically the process that we're going to do every time that a trig substitution integral comes up. And so I guess the main part now is recognizing the integral that you have and noticing that it could be turned into a function of theta. So I think the key to noticing that is kind of when you have something involving a square root. You know, it might be a 4 plus x squared. It might be 16 minus a y squared. Anything with a squared term inside of a square root, it's possible that because of the way Pythagorean theorem works, you could turn this into a trig function. So I would keep an eye out for that and try a bunch of examples. Try as many of them as you can. Once you get the hang of it, all these sub-steps that are involved, even though there's a lot of them, it's nothing that you can't do. It's nothing that you haven't learned already. Yeah, good luck. Let me know if you have questions.